Thank you so much. Thank you so much for this kind introduction, and of course, also thanks a lot for inviting me to this very nice workshop. It's really a pleasure for me to be here, although very sadly it's only virtual, but at least like we can do this via Zoom. So hopefully you can see my screen and you can hear me well. Okay, so first of all, let me say that what I will speak about today, I didn't do just by myself. It is collaborative work with two great colleagues, former colleagues from TU Berlin. So these are Jan McDonald and Max Merz, who at the time when we did these projects were both still PhD students. So Max graduated in the middle of this year and Jan will submit his thesis, I think, in a few weeks. And I think it's really fair to say that they did an amazing job in these projects, and without them, it wouldn't have been possible. All right, so, well, as this will be a bit longer talk, let me give you a brief outline of what we will speak about today. So as the title already suggests, this will be about inverse problems and also about how to solve these inverse problems with deep learning. So I will give you a very brief overview about this, how you can do this. And then we will turn to two really foundational aspects of such methods, not only for learned methods, but here we will focus on them, namely on the aspects of robustness and accuracy. And when it comes to accuracy, I will particularly show you a case study that is related to a recent deep learning challenge that we have participated in. And finally, there will be a quick conclusion. Okay, so by the way, if there are any questions or so, if something's unclear, please feel free to interrupt me. So right now I can't see the chat, but yeah, so hopefully, I mean, if there's anything that's unclear, please, yeah, feel free to interrupt me anytime. Okay, so let's get started. So, I mean, I think you're quite familiar with inverse problems. So, well, you have seen this before, so I think it does not deserve much motivation, and I think clear to everybody that inverse problems play an important role in many different real-world applications. And well, what I want to say here that in this talk, we will focus on an important subclass of inverse problems, which are discrete, which means finite dimensional ones, and also the ones that are linear. So basically the slide that you see here is just like a repetition and the one to fix the notation for the rest of this talk. Okay, so basically the inverse problems that we will consider will take this form here. So there's an unknown signal, typically high dimensional, think of an image, for instance. And the point is that this signal is not measured directly. So we don't observe it directly, but only in terms of some indirect measurements, which are measured by a linear forward operator, which here basically is just a matrix. And as usual in real world applications, these measurements are contaminated by noise. So there's some additive term here. And here in this talk, we will assume that there's some prior knowledge, at least, of this noise in terms of the energy. So we assume that there's a certain upper bound on the power of the noise, which is measured in the LT norm. And then the question is, can we recover this unknown signal given the measurements? Okay, so that's the basic setup. And this becomes particularly interesting if some information is missing, in the sense that we have less measurements available than unknown variables. So the problem becomes ill-posed, and without any further assumptions, it's not possible to come up with a unique solution. So a good example, I think, is the in-painting problem, where some information from your image is removed and you need to fill this in somehow. Okay, so basically we are concerned with this quest for unique and also stable solutions to these inverse problems. All right, so let me give you two more examples that will particularly also reappear in this talk as like running examples, prototypic examples. They are both from medical imaging, two different imaging modalities. So the first one is MRI. So basically here the forward model, very simply speaking, corresponds to taking frequency measurements, and the question is how to go back, right, to reconstruct an image. And the other one that I will also show you here in this talk is, well, inspired by computed tomography. So here, basically, the measurement, the forward model is taking line integrals in different angles. So basically, you measure some projections. And again, the question is how to get back. Well, and I spoke about like missing information. And here, I particularly wish to point out that subsampling is desirable in both regimes. So typically what you don't have is like access to the full measurement space, but only to a smaller subset, right? So that's the idea of compressed sensing. So for instance, you only have a subset of frequency measurements or a subset of line integrals. And this makes this certainly more difficult. And the question is, can we still come up with a good solution to this inverse problem? Okay, so these were the two examples. Now let's really just dive into the idea of deep learning for inverse problems. So conceptually, I would say it's quite simple. So what we're interested is in a reconstruction map, of course, so which maps measurements from the measurement space to the signal space. And hopefully we're able to compute a reconstruction map that for some unseen pair of data from an inverse problem gives you a good reconstruction. And the point is, because this is learning, that this reconstruction map is parameterized. So there's some set of learnable parameters. And the question is, how can we compute those that particularly give us this nice generalization property? So typically you can do this if you have some training data. So this is very briefly summarized here in this box. So here we will only focus on the supervised learning process. So we assume that we have a probably large set of examples from the inverse problem, which are pairs of measurements and ground truth images. And then the question is, can we solve an empirical loss minimization problem? That means we would like to compute that parameters of the reconstruction method that fit the data as well as possible. And the hope is that this also generalizes to unseen data. So that's the basic idea. Quite simple and quite straightforward. I mean, deep learning is about deep neural networks. So basically, you can think of this reconstruction map as a neural network, and these are the parameters of the neural networks. This parameter vector or set of parameters theta. The point is that this might be a very complicated map. So these neural networks might be very expressive. It is nonlinear. But an important point here is that this is explicit, right? So it's an explicit map, and you can evaluate this typically very quickly on your computer. So that's a huge difference to classical variational approaches, where you often have to solve some more complicated optimization problem. And also what is, I think, quite different here is that the fact typically there's no prior knowledge about your inverse problem involved here. So you try directly to infer the information, the prior knowledge about the kinds of signals that you're interested in from the data, right? So that's the idea of data-driven mechanisms. Well, I mean, here you see like this illustration of a neural network. So that's very schematic, but I should say that for inverse problems and in practice, typically what you have is that this map rec is a combination of convolutional neural networks and some model-based components. So to make this a bit more precise, let me give you a very simple example. And actually, that's the one that, to the best of my knowledge, was actually the first method that was really like became popular in the literature on deep learning for inverse problems. So it's called Postprocessing Network. And well, this picture, I think, very nicely explains why it is called this way. So what you do here is, like for this MRI problem, you first, from your measurements, use a very cheap inversion, which could be like the inverse Fourier transform, when you zero fill your data. So this will give you a very cheap, very quick model-based inversion, which certainly has some artifacts due to the undersampling. And then the idea is to just learn a neural network that enhances these images of artifacts to give you hopefully a good, clean reconstruction. So basically the purpose of the neural network, which you learn, is to remove these artifacts, right? And I mean, I'm speaking of convolutional neural networks. So typically these are not just a few convolutional layers, but something more sophisticated like the unit, which you can see on the right-hand side. So I won't go too much into details here. So basically, it's a fully convolutional network that maps images to images, and well, it's like has this encoder-decoder structure. It involves like subsampling and also has many skip connections and gives us this typical U shape, and this explains why it's called the unit. So I'm mentioning this here already because this will also play an important role later on in the methods that we considered in our projects. Okay, so the main idea is like really a two-step procedure. First, a cheap model-based inversion, then something that is learned. Okay, so that's just one example. So basically in this overview slide, I'm giving you some references, and by far this list is by far not complete. So really after this hype of deep learning, started in particular in risk problems, which was about 5 years ago. We really observed like an explosion of works presenting different types of approaches and architectures to solve in risk problems. There are thousands of papers. So here in this talk, also for time reasons, we will only focus on two very popular approaches, which are these post-processing networks that you've just seen on the previous slide, and something that is called unrolling, and I will go more into detail on this later on. So what is important here is that these two types of networks are really what I would call end-to-end. Like there are, like if you have this picture, they are really like architectures that take a measurement and give you some reconstruction. So there's no optimization or such thing involved here, right? So really just a reconstruction from measurements to the signals. Okay, and I think it's nowadays fair to say that, well, neural networks form the state of the art, at least for many types of in-risk problems, in particular when it comes to image quality and also speed. So one might ask now, given these this huge amount of works, whether this gold rush move is over. So I would say in some sense that might be true, because I think right now it's really like that architecture-wise, the field is in a very mature state, and it's, I would say, quite hard to contribute with new, very innovative architectures. But, and this is what I will also focus on in this talk, I think there are still many interesting questions open, in particular when it comes really to the foundations of solving in-risk problems with deep learning. Okay, so to motivate us a bit, let me give you a very quick comparison between like these deep learning-based approaches, which I've just introduced, and classical variational approaches, which I guess you've seen before. We also saw this morning, like what you would typically do if you solve an in-risk problem with a model-based approach. So here, well, first of all, I just said this, like one thing that is in favor of learning-based methods is that they often produce better and more accurate results. And something that is very nice, they're often explicit maps, so they give you very fast reconstruction, which stands in contrast to variational approaches where you have to solve this optimization problem, which typically also, at least in some sense, suffers from this handcrafted regularization term, because there might be a mismatch between the actual types of signals that you're interested in and the prior that you have chosen. So maybe you can think of like sparsity is a very good prior for natural images, at least with respect to a certain domain, but it might not be a perfect prior. Okay, so that's one thing. The other thing, of course, there's a price to pay for this gain, and really the price here, I think, is the training, which is typically very expensive. It requires good, high quality data. Well, and if you have this, I mean, you can really train these new networks to get a state-of-the-art performance, but that's very task specific, right? So you really get something that fits your data well and adapts to the data, but it's really specific to the task that you have at hand. In contrast, these variational methods are typically universal, right? So you can like use things like total variation minimization in many different image modalities, many different regimes. So they are really like universally applicable. However, I mean, also here there's some hidden cost, like which is typically manifests in choosing the hyperparameters, which here in this case would be this parameter limit. So this is also a non-trivial task. Okay, so this brings me to the last point, and this is really what also motivates the rest of this talk. So one big advantage, I would say, of classical model-based approaches is that they are quite well understood when it comes to theory. So often these are convex optimization problems, and they enjoy a rich theoretical foundation. So here, I mean, is like an error-bound, prototypic error bound, I would say, that you would like to have. And I mean, if you go to books on compressed sensing, you'll indeed find bounds like this for many different approaches. So, well, it's about like how good the reconstruction quality is. And I think it's natural to decompose this term into two different expressions just by the triangular inequality. So the first one is associated with accuracy, which basically measures how well your method is working in the idealistic situation of noise-free data. So how good does it become if the measurement is perfect? Okay. And the other thing is robustness, which basically means how sensitive is your method against noise, right? So we have assumed that there's some additive noise, and of course, it's a very important question to understand and to control this term. And ideally, what you would like to have is an error bound of this form. So you would like to have control in terms of this noise bound, of the power of the noise, times some maybe unknown, but hopefully small constant. Okay, so that's one thing. The other thing is that, on the other hand, unfortunately, many of the deep learning based approaches still have to be considered as black boxes. So there's no really like fully comprehensive theory for this, that which would give you really like strict error bounds of this form. So the question that I wish to ask is, how reliable are these neural networks really? So in particular, if you think of medical imaging application, this is really a crucial thing to understand, right? Okay, so that basically finishes this introduction. And now I will, basically focus on these two terms. So I will start with the robustness term and then move on with this case study and this AAPM challenge on accuracy. Okay, so let's speak about robustness. Well, before I actually get back to inverse problems, let me start with some motivation where this whole deep learning hype has started, which is undeniably in classification. Right, and if you're a bit familiar with this area, you may have also heard about adversarial attacks, which quickly came up in the literature after this hype started. So basically, what this means is that in many cases possible to like fool your neural network with some almost imperceptible perturbation to the input. Like we have this classification of the punter here, right? And it's indeed possible to compute some perturbation of this input, which is imperceptible for us as humans, but fools the network with very high confidence. So it gives you like this given with almost certainty. Okay, so this is indeed a huge issue in the field, and it also transfers to real-world applications like autonomous driving. So it's really a serious thing there. And more technically, what you exploit here is like this discontinuous decision boundary. So what you would like to compute is a perturbation of your input, which is as small as possible, measured in some distance. And well, it should cross the decision boundary. So it should lead to a different class. So basically, this is how you would compute such adversarial perturbations. Okay, but the question is actually, does all this carry over to the field of inverse problems, right? Which is, I mean, as you can easily see, a different setup than classification. Okay, so as a matter of fact, there are much fewer works on this in the literature, but there are a few indeed. And the one that I particularly wish to mention here and was also inspiring for us is a recent PNAS paper by Anton et al. And well, in their paper, they made some worrying findings. And the picture that you can see here is taken from their paper. So basically what they considered here is an MRI setup, undersampled MRI. And well, they basically computed adversarial perturbations, so some perturbations to the input, such that, well, the reconstruction error of a certain neural network, which here is a pre-trained automap architecture, it's an end-to-end architecture, well, the error of this method gets as large as possible. So basically, well, what you see here is the input. So that's the perturbed image. So you can see a bit of noise here, right? And then they measure this, they take the measurements and let the network do the reconstruction. And suddenly you see these clear artifacts. And their conclusion was, well, this is really like an instability and one should be worried about this. And this was also like recognized even by medical doctors, like, well, it was confirmed what they have believed before, that also these neural networks for inverse problems are vulnerable against adversarial attacks. Well, so this is an alarming finding, and also at the time was like the starting point for our project. We found this very interesting, and well, there were a few questions that we asked in the beginning that also motivate our study. So the first one is, I already mentioned this before, the fact that solving inverse problem is a very different task than image classification, right? So even if you consider the input and output domain of both tasks, you see it's very different. Like for inverse problems, you have high dimensional inputs and high dimensional outputs, and that's very different from classification. In particular, for classification, it's clear what you exploit in the attack, which is this somewhat brittle decision boundary. Okay. And on the other hand, for inverse problems, at least for us, it was not clear what an attacker would exploit, right? So what makes these methods unstable? The other thing is that, as you will also see in a few minutes, many new network architectures for inverse problems are inspired by classical model-based algorithms, which are often provably robust. So the question is, what makes the learned methods different from the classical model-based methods? So are there some numerical instabilities? And finally, and I think this is the most important point, like the pictures that you've seen, they are mostly of qualitative nature. So you won't see any numbers, any errors there. It's basically just some shocking pictures. And the question is, can we do this more quantitatively? Can we come up with some benchmark setup that really allows us to see how bad the situation really is? And in particular, I mean, I've shown you these error bounds before. For inverse problems, we have a much better understanding of what robustness actually means. So what a method should satisfy to be robust. So, well, the question was then, like, are these deep neural networks really as unstable as these previous findings suggest? Okay, so that was the starting point. Now let's speak about the case study that we conducted. Before I can actually show you some results, we need to speak about technical aspects, in particular about the kinds of new networks that we considered. So here we really try to come up with a representative selection of end-to-end architectures. So the one that you see here on the screen now, you already saw before, it's just this post-processing approach. It's actually the most simple thing that you can think of. It's this two-step procedure, and here we really use this unit as the computational backbone. So that's the component that is learned in the neural network. Of course, when you can extend this, so what you could do, for instance, is you could replace this model-based inversion by something that is still linear, but you can make this learnable, right? So, I mean, this is basically a linear operator. You can make this learnable and hopefully come up with a better initial step before your actual network is applied. And also, of course, this unit architecture, it's very popular, of course, but I mean, you're not restricted to this, and you could try something else. And what we also considered is the so-called tiramisu, which is also fully convolutional, but well, involves also some dense blocks with more skip connections. So basically what you can think of is a more powerful unit here. So you would expect that this method really is more expressive and performs better. And finally, this is like our flagship method. It's also not like a new invention. This is an iterative network. So the idea here is also, I think, quite simple and natural. So what you do here is, again, this linear inversion step, and then what you have is like a cascade of signal enhancement, so similar as before. And then this is like followed by some data consistency terms, and you have these loops. So you iterate this. And if you're a bit familiar with optimization, also for classical variational methods, this might appear very familiar. So basically, this is inspired by classical proximal gradient schemes, where this data consistency term is just an L2 gradient step of a proximal gradient scheme. And what is replaced here by something learnable is the proximal operator. So this is where the role that is played by the unit. Okay. So, but conceptually, the idea is quite simple. So you have this like learned signal enhancement that alternates with a data consistency term, and you would hope like that this gives you better results. What was very important to us was that, like, for the training, we really stick to the standard approaches. So what we did is we solved this empirical risk minimization problem with mini-batch stochastic gradient descent in combination with the popular Radon optimizer. And we didn't involve any adversarial defenses or such things. So these are really like standard end-to-end neural networks that we trained in-house. Okay, so that's about the architectures. The other thing, of course, is how do we actually measure robustness? So this is what this slide is about. So, well, you've seen these adversarial attacks for classification, and the idea that we pursue is quite similar. So we would like to compute that perturbation of the input, and the input here is basically just this additive noise D, that maximizes the reconstruction error of your given method. So, well, we have this constraint, of course, and because the inverse problem, like we assume this constraint, we have to respect this constraint, but within this constraint, we would like to compute the worst possible perturbation that maximizes the reconstruction error. So basically, this looks like a simple problem, but it turns out it's non-convex. So we don't have any optimality certificate here, and well, we have to carefully tackle this problem. We did this by projected gradient descent in combination again with ADA, and making use of automatic differentiation and so on. Okay, but that's of course not the whole story, because if we have such an adversarial perturbation, it's still not so clear what to do with this. We still don't have this benchmark, this comparison study. And that brings me really to the key point of our study, which was to say, well, if we would like to have something to compare this to, we should rely on something that we understand better. And well, what we understand better for inverse problems are classical model-based approaches like total variation minimization, which you see here. It's a simple variational approach which encourages gradient sparsity. Okay, and we know that in many situations of interest, this is a robust method in the sense that it satisfies error bounds like this. Right, so we may not know this concept, but at least we know it's a robust method. So the idea was to say, well, maybe we can also perturb TV minimization. We can compute the worst possible noise for such methods as well, to really find the boundaries, the limitations of this bound where this becomes sharp, right? And then we can compare these perturbations to what we have computed for the neural network. Right, so this is like a benchmark. So that's the principle that we follow, is we would declare a neural network as robust if it's similarly, the error is comparable to the one of TV minimization. Okay, so that's the main idea, computing this adversarial noise for classical method. Again, this sounds simple, but this really was the main technical challenge of our approach, because so basically what you would have to do is you would have to solve this problem for the TV problem. So you would replace net by TV, and it becomes a bi-level optimization problem. It's not so obvious how to solve this with satisfactory precision. And one of the main tricks here was to do a careful unrolling, so come up with an iterative scheme for TV minimization. Okay, so that was basically the technical basis, and now I'm happy to show you some results. All right, so let's start simple. So that's actually the most basic setup that we considered. It's about a standard compressed sensing setup with standard Gaussian matrices. So it's an undersampled setup. We have less measurements than free variables, and we considered piecewise constant signals with random jumps. So here's a typical example, right? So it's synthetic data, and you can basically generate as many data as you wish. Okay, so, well, let's see what would happen to TV minimization, right? So if you don't have any noise, you will actually get zero error, because TV is a perfect match for such gradient sparse signals. So that's really backed up by theory. And well, then you could increase the noise. So we measure this as a relative error here to make the results comparable. So you increase the noise, and of course also the error will increase, and you also will see some visual perturbations, some errors in the reconstruction. And if you increase this, of course, the error will become larger and larger, and already at 6%, you will realize, well, actually, this is not a satisfactory solution anymore. Although this might really respect an error bound, basically, this is too much adversarial noise. So we can stop here. If even the robust method produces some crap, we don't have to go any further here. All right, so what is more interesting then is what do the neural networks do? Okay, so in the noiseless case, you won't get perfect recovery, which is an interesting aspect, and I will come back to this in the second part of this talk. But what is really, I think, surprising also given these previous works is that, well, if we increase the noise, the error does not suddenly explode. It actually is comparable to the one of TV minimization, even a bit smaller, and also qualitatively, like the reconstructions or the perturbations really look very similar. And it only becomes better if you apply this to the more powerful networks like the fully learned one, which you see here, or even the iterative neural network, which typically gives you the best results. Okay, but these are again just some pictures. Let me make this more systematic. So what we were actually interested in are these noise to error curves, which you can see here. So they are really like evaluated over a whole set of test signals. So basically this confirms what you just saw on a previous slide. So we plot the relative noise level of adversarial perturbations against the reconstruction error, and you can clearly see like that the robustness of the networks is comparable to the one of TV minimization. So in that sense, after our basic principle, we can declare these neural networks as robust. And also what is quite interesting is to compare this to what you would obtain with statistical noise, right? So that's just Gaussian noise of the same power, of the same two normal, at least in expectation, and you can clearly see the gap between adversarial and statistical noise. Okay, so there's no time to show you all the results that we have in detail. So basically this slide is just an overview. Well, we repeated basically this compressed sensing setup for something that is a bit more complicated. That's the MNIST data set. So what is remarkable here is that TV is not a perfect match anymore. So you clearly can see that TV is outperformed by the neural networks, both regarding accuracy and robustness. So these curves are strictly below the one of TV minimization for any noise level that we considered, right? Because the networks simply adapt better to the problem that you have at hand, which here is reconstructing MNIST digits. Then we moved on to much higher dimensional data. So that's a setup that is like simulated MRI. So we have subsampled frequency measurement, but still with synthetic data, which are these random ellipses. So basically that's the counterpart to the piecewise constant signals that you've seen on the previous slide. And also the curves are very similar. So again, TV is a much better match. And you will see that the robustness of the neural networks is comparable to TV minimization. And finally, like that, also some real world data. Here we relied on the nowadays quite popular NYU-fastMRI data set, which consists of a few thousand MRI knee scans. And basically this confirms, so these curves confirm what you just saw for MNIST here, but here in a much higher dimensional setup. So again, TV minimization is outperformed by the neural networks regarding both accuracy and robustness. Okay. Okay. So, well, to close the first part, I at least would like to show you a few more aspects about this. So, well, let's maybe have a closer look at actual reconstructions that would correspond to what you see in these curves. So this is the one for the fastMRI data set. So here again, we increase the noise level. And what is quite interesting here, I think, is that for TV minimization, basically what the attack is doing, it amplifies known flaws of this method, which here is this oil painting effect, which is quite well known for TV minimization. Okay, so that's maybe not too surprising. What is remarkable is that for the neural networks, all the reconstructions, no matter how high the noise level is, they are basically, they look like clean images, right? So, I mean, they all look very nice, like good reconstructions. And what you see here, I mean, like the difference is then, that's also why the error is increasing, that the attacker in some sense adds some features to the data. So if you look at this outside fat region here, you will see that some structure is added, like this vessel structure here. Right, so that's what changing if you go on with higher noise levels. Okay, so well, that's just an observation, and now you might be worried: is this some kind of instability? Is this something well that is alarming, or what is going on here? Okay, so well, for this, let me show another experiment. So that's for the ellipses, but basically you can also reproduce this for this fastMRI setting. But I think it becomes a bit clearer. So again, you see some perturbed reconstructions, again, for the highest noise level that can be considered for these ellipses. So the one for the iterative network and the one for TV minimization. Again, you can clearly see this oil painting effect. And what we did here is to say, well, we've computed some perturbations, some attack for the internet. What happens if we would plug in the same perturbation, the same measurement into TV minimization? And what you can clearly see here is that actually the same artifacts, the same features appear with this method as well. It's a completely different approach. It's model-based, but you can clearly see the same picture. So our conclusion here was, well, basically what the attacker did is it took the noise, this 8% relative noise, and synthesized some features in the measurements that were then eventually reconstructed by your solver, which are here the internet and also TV minimization. So in some sense, that's really like what I would call the essence of stability. Like there's no instability, like the attacker really took the noise and synthesized some features, right? So that's really something stable in that sense. And remarkably, basically the picture, the reverse experiment does not succeed. Like this oil painting effect does not transfer to the internet. Although if you look at the errors, that's very similar. So you should be like confused by just looking at these visual reconstructions here, right? Another thing that I would like to show is like, also you might wonder, so how does our setup compare to this original paper from Anton et al.? So you might say, well, it somehow contradicts. So I think it's rather not like that there is, from a technical perspective, a contradiction here. So this is why we also like basically repeated their experiments in our setup. So what we did is like really, we computed these perturbations in the measurement domain. What they did is just to have a visualization, they translated this back to the image domain. This is possible, for instance, in this MRI setup, because what you could do is you could just like zero fill your missing measurements and then take the inverse Fourier transform. So this is basically what you see here, these pictures, and also here at the top, right? And well, what you can also see with the same setup as here in this transferability argument, just looking at these pictures is somewhat like, it might lead to different conclusions, right? So in both cases, I don't know if you can see this via Zoom, you won't see many like changes to the original images. Maybe you can see like these small ellipses here. For TV, basically you can see nothing. And suddenly, if you measure the data and do the reconstruction, you'll suddenly see these oil paintings or these additional features, right? But what I want to say is that this is perfectly fine. Like it's really a fact of life, right? So you have a large kernel, you have some subsampling, and basically it's, if you just look at the images, you might think these are some instabilities, but hopefully I convinced you also with these curves and this transferability experiment that these are actually not really instabilities, right? So it's just like simply what is happening here. Okay, so this closes the first part about robustness. And in the remaining time, which will be like the shorter part, I would like to show you some results that we have on accuracy. Okay, so well, let's take a step back first. So basically what you see here is this error bound that I've shown you in the first part. It's this decomposition in accuracy expression and robustness expression. So the previous part was mostly about this thing. And now we would like to speak about accuracy, which essentially means that you are interested in the limit case where this noise or the noise bound tends to zero or is actually equal to zero. So these are just pictures that you've seen before. So accuracy essentially corresponds here to the left end of these curves, right? So the cross section that you would obtain at the left end of these curves. And what is, if you have a close look at this, what is remarkable is that indeed the only method that can really achieve zero error, at least in the situation of gradient sparse signals, is TV minimization, right? So here it's really like almost exactly zero or up to numerical precision. And for the neural networks, you don't observe it. Like, so they give you good reconstruction, but not perfect ones. So I think a fair question is to ask, so what are the neural networks doing here? Shouldn't they be able to give you also perfect reconstruction, because we know there exists a method that can do the job? Can neural networks do the same? So this question was, we were not the first to ask this question. Actually, this was considered in a very nice work by Emil Sidki and co-authors. So they focused on this computed tomography setup, a sparse-view computed tomography to be more precise. So there's some subsampling involved. You don't take like the full angles for your line projections, but only a small part of them. And what they found in their work is indeed, for simple post-processing methods like the unit project you also saw before, the answer is no. You can't achieve like almost zero error here at the left end of these curves. Right, so the data that he considered is like simulated data. It's basically gradient sparse. It's simulating breast CT data. So here's some examples. And what they found is that TV indeed can produce near exact solutions, while simple CNNs, post-processing CNNs can't do this. So maybe you can also see here via Zoom that there are some visual differences between these two reconstructions. And this motivated them to initiate a challenge, to seek for the data-driven methodology that provides the most accurate reconstructions in this Sparse-View CT data set. So that was a challenge that took place in the middle of this year. And well, because we were working on this anyway with CT and MRI, and we were quite interested in this, so we decided to participate. And well, a few more details about this. What was actually the setup here? So they provided like data like this, so simulated data, and in total were 4,000 images, pairs of ground truth images and sinogram measurements, right? And the error was measured in a normalized version of the mean squared error, and basically the time frame for the challenge was from really release of the training data set to final submission of the test results was about 3 months. And finally, about 60 groups participated, and I think 25 of them really submitted their method in the final evaluation. Okay, so that's the setup, and what was really distinctive here, and also quite like challenging in a way, is that the forward model was not provided to the participants. Right, so it was known that it's like a CT, a fan beam geometry. We'll see a picture on the next slide. But the exact configuration, the exact parameters were completely unknown, right? So what you only got were really like images, ground truth images, and the measurements. So basically both directions, A and also of course the reconstruction, were unknown. Okay, so that was the setup. And well, because like what they found in their previous work is that simply post-processing is not enough. Well, we had this initial hypothesis, you have to, in some sense, incorporate a forward model to come up with more accurate solutions, to really push the error to almost zero. I should say, I forgot this to say, like, very important here, the data, the measurements here were really noiseless. It's really like the situation that I've described here, like they were really interested in the situation where the data, the measurement is completely noiseless. So there's no noise involved here. Okay, so well, let me get back to this. So the idea was that well, we need to incorporate the forward model to apply approaches like our iterative net, for instance. But the point is, as I said, the forward model was unknown. So the idea was to say, well, we know it's a fan beam geometry. So what we did is we basically implemented this fan beam forward operator from scratch in PyTorch. So basically implementing this picture, computing these line integrals and so on and so on. And because it was like in PyTorch, we could make use of automatic differentiation and basically estimate the unknown parameters given the challenge data. So this is what we did in the first step. So this has nothing to do with image reconstruction. And yeah, so it's not really like deep learning because there's no neural network involved here, but basically the strategy was inspired, like making use of backpropagation and automatic differentiation. And well, applying some tricks, we were indeed able to infer the forward model very accurately from the data. So you can see some filtered back projection results, the one that were provided directly by the challenge and the one that we estimated. You can already see like that we even got a better reconstruction here, although this is certainly not enough for accurate reconstruction, but just to give you an impression. Okay. That's cool. We have now a forward model, or at least a very good estimate thereof. And what we then is basically, you saw this in the first part of the talk, we applied the methods that we already used in our robustness case study. So, well, what we first did is to, train this post-processing approach, where we already know that this won't be enough, but we did this anyway. So that's basically this two-step procedure. And we only did this to have a good warm start for our iterative network. So that's really the network that you've seen before. It's this loop of data consistency and signal enhancement terms. And well, why did we do this? Because I think hopefully this becomes clearer with this image here. With this good initialization, so basically we use these unit weights that we obtained from this first training step as an initialization for this one here. You can clearly see the difference, or what would have happened if we wouldn't have done this. So these red and green curves, you basically correspond to the loss that is without any, or with random initialization, that the orange and blue one correspond to our approach with the warm start. You can clearly see a huge jump in the accuracy and also like the conversion speed in the end. So that was the purpose of this pre-training step. Okay, but in the end, we really had this iterative network, which of course makes also use of the forward model. And one point, I mean, that's a detail, but it's an important detail. One point that I should mention here is that instead of just using the adjoint, which would be like what you would get from a theoretical consideration, we made use of the filtered back projection here. So it has some advantages, in particular because like gives you already a better reconstruction for this data consistency term here, and the reconstruction is actually like this model-based reconstruction is already at the right scale, the right pixel scale. Otherwise, you would have to apply some normalization. Okay, so that was also like an important trick that we applied here. Okay, and there's many more, but I won't go into details. All right, so that's our approach, and now I'm happy to tell you that we actually won this challenge. And so here you see like the final leaderboard, and as a matter of fact, we really, I would say it's fair to say that we won this with like a considerable margin. So the second place here is like outperformed by a factor of 5, and I think the third place by a factor of 20. So that's like what we achieved, is 10 to the minus 6. Okay, it's a bit hard to compare because it's just a number, but I mean, you can see like the other reconstruction accuracies here, like for the post-processing approach or other state-of-the-art approaches, you can clearly see the gain in accuracy. And in fact, this number is really comparable to what you would obtain by TB minimization. So from a practical perspective, one could say that the problem is solved up to numerical precision. Okay, so that's one thing, but also conceptually, like what we have learned and or what we were able to conclude is that indeed we can give a positive answer to this accuracy question. It is possible to compute near exact solutions by deep learning techniques, although maybe zero error might be possible in theory, but at least from a practical perspective, we could consider the problem as solved. Model-based knowledge was very important. I hope this became clear. And also, I mean, this architecture that you've seen here, it's conceptually quite simple. So what was really like more important is to have a good understanding of how you should train your neural networks, like using all these tricks with a good initialization and so on, and also understanding the data. So that's what you learned is more important than using super sophisticated architectures that are well motivated by theory. And finally, and this is really, I would say, the most remarkable fact is here, like the number of iterations here is really just 5. So to achieve this really almost perfect accuracy, we only need to evaluate the forward model 5 times. So for instance, TB minimization in this case would require hundreds or thousands of iterations, which of course is computationally much more challenging. So that's really like surprising that to produce such results, you only need a very few iterations or evaluations of the forward method. Okay, so that ends also the second part, and now I'm also running out of time. So there's one slide left about the conclusion. Okay, so these are the main take-home messages. So what we've seen with these two case studies is like, indeed, deep neural networks show us one response can be robust against adversarial noise, and they can be also accurate. And well, as I said, like careful training is really, really an important aspect here. So the architectures are not so important. You can use like standard architectures based on unrolling. And in particular, to have this robustness, we didn't make use of any adversarial defenses. So this was really like standard training. And well, conceptually for these studies was what was really important in both cases, I would think, to have these benchmarks like TV minimization in our cases, but in other studies might be something different, but really to have something, a baseline to compare to, right? So that was really, really the key here. And in particular, one should not be to put too much off like just looking at these images. So there might be something different, sometimes different conclusions than looking at these noise to error curves, for instance. Well, but of course, this is not the whole story. Like, I mean, I would say that these observations are really just minimal criteria to, well, they're necessary to have hope for reliable neural networks in applications, but there are many open questions that should be studied, I think. Like what for me at least is very striking is this gap between classification and reconstruction, right? So why is one regime more vulnerable than the other? Also, what would be very interesting to explore more, and this is a very active research field, is like what happens if you go out of distribution, if your image that you're interested in is quite far away from the training data, right? So this becomes particularly relevant if, well, there are some features in the data that only rarely appear in the training set, but they are very important. So that was one thing that was realized in these fast-MRI challenges. Also hallucinations, which is the fact that sometimes the network like synthesize some features that are actually not present in the measurements in the data, right? So a hallucination. And well, and this is, I think, a main difference to classical methods. It's really hard to detect them. As I said, neural networks typically always produce nice looking images. So it's really hard to say when was a neural network perturbed or attacked by somebody. Even though it might be robust, it's not so clear, right? For TV, we have seen this oil painting, for instance, but for the neural networks, it's not so clear. And finally, of course, it would be nice to have like theoretical certificates, right? So these tests that we have seen here, they are expensive, right? So, I mean, you saw these nice curves, but it took much time to compute these curves. And would be, of course, much better to have like some theoretical and cheaper certificates that would give us basically the same guarantees of robustness. That's an open field, and I think something very interesting that could be studied in the future. Okay, so I think that's all I wanted to say. Thanks a lot for the attention. So the papers are in the archive. Also, the general challenge report, the code is available for both projects. You will find them on Jan's GitHub profile, and I'm happy to answer your questions.
Okay, thank you very much for this very interesting talk. Are there any questions from the audience? Yes, Jan has a question, so please go ahead.
Yes, thank you for the very clear talk. And my question is about I think your last slide, and I think that there is a main difference between robustness. I'm not sure I'm 100% all right with the definition of robustness from TV extended to the neural network. Because, as you said, like the neural network will depend on the training data. So, so in this robustness term, as you said, you produce noise which is noise which is dependent on the data. So, have you started to or tried to look like if you include like the knowledge of the training on how was trained the network in this robustness bounds.
So let me so maybe I so hopefully I get your question right. So let me go back to the attacks, right? So that's the question is about how do we compute the attacks. So I should say like that this whole procedure, how we like measure robustness, is not related to the training data set, right? So basically what
the network is related to the training data set.
Yeah, of course, we compute
that is the biggest difference. That's why I think there's like some it's like in the TV case, the error you produce, the robustness error, is fixed and only depends on the function, the choice of the function. Here, the robustness error will depend on the data. Is data dependent.
But
so,
the data, when like the data that we like, the signal or the measurement that is perturbed is not from the training data set. Could be anything. It's from the test set.
Yes, but it should be drawn from the same distribution or the same low dimensional model if you train correctly. And when you do that, I think that you can you very quickly fall on something that is not very robust with respect to if you try to learn a low dimensional model. That's I mean the part that you did, it's really necessary to have robustness, but it's in your last slide, like if
like out of robustness,
it's
here it is. Okay, so now I think I get it. So your point is like, I mean, what would happen if there's some signal that is far away from the training data distribution, and that's a fair point, right? So it's not that well understood. I should say we have some experiments in our paper because some of the reviewers specifically asked us to do some experiments. So I would say the situation indeed is not as bad as you might expect. So we don't have like such systematic studies for this, but we made some interesting findings there. So if you're familiar, for instance, with this paper from Antun et al. That I've shown, they also have some experiments about like what happened if you add some features like text to your image, right? So right. So something that the network has never seen. So basically, we did this in this ellipsis setup. So we added some text to the data. The network has never seen this. And indeed, if you carefully train your neural network, like not for the text, but it turns out it is still able to recover the text. That's something, for instance, I mean, it's not well understood, I should say, but at least we got some positive results in that direction.
I don't know if they are the same authors. There are the papers by co-authors of Bernard Koch as
well.
Yeah,
it's that paper.
Is that?
Yeah.
But they show that they, when they reconstruct, they miss things, no?
Yeah, that's right. So that's like, I mean, this is what I say. It's not so clear anymore, right? So there are some networks that can do this. There are some networks that can't do. So what we learned is like that this iterative network can do this. So I should say, like in this study, that was also one point that was like important to us. We trained all the networks in-house, right? So basically they took some pre-trained models and like, okay, maybe you have to adapt the training process a bit, but in principle it's possible. But it's a very interesting point. Like,
and from what I investigated, like theoretically, like it might be very important to have some kind of a regularization of the weights during the training. So do you have any regularization of the weights?
Yeah, we do. We have weight decay, like it's an L2 penalty, right? So that was important for as a regularization, and also like required some hyperparameter tuning. But I would say it's still standard, right? So I would say like many people are doing this to train their neural networks, having weight decay.
Yeah.
Was also relevant for us. Yeah, but that was the only kind of regularization, explicit regularization that we had. Yeah.
Okay, thank you.
Welcome.
I think Laurent also has a question.
Yes. Thank you, Martin, for this very interesting and clear presentation. I have a question with respect to also the robustness analysis you realized. I was wondering if you think that the conclusion of your analysis will remain the same if the inverse problem you consider is a little bit more difficult, and if it is nonlinear, for instance, like in phase retrieval or in one-bit compressive sensing. Do you think that some of the analysis you have realized here are really connected to the fact that the sensing operator is linear or not?
Okay, good question. That's a good point, right? So, I mean, I can't give you a final answer here because like that were the setups that we considered, but it would be very interesting, like to see what would happen if like there's some nonlinearity involved, for instance. So what I think is, and this is also related to a work of Ben Adcock and co-authors, so that's a different paper. Like what they pointed out is that there's this trade-off, like about the ill-posedness of the problem. Like if you would take too few measurements, basically reconstruction and robust, accurate and robust reconstruction becomes like mutually exclusive, right? So if you make the problem more complicated, and that's something that the new networks can't escape. So I think basically there are two situations or two things that I would expect that you would observe if you make the problem more complicated. So the first one, this is why I'm showing you this slide, is like that, well, you may get robust methods, but like the accuracy will decrease, right? So the left end will start at a higher point. You won't get that good reconstructions anymore. For instance, for the fastMRI data set, if I go back, I mean, you won't get zero error even if you're noiseless, right? So, I mean, that's a more complicated problem, right? And the other thing is this is just a conjecture. We had a few observations in that direction, but I think what I believe is if the problem is actually too ill-posed, my conjecture is that already the training process becomes unstable, right? So if basically, I mean, like you can't really solve the problems because it's impossible from theory, right? So you have too few measurements, let's say, or so it's simply too nonlinear. I guess that you won't be able to really train a good neural network. So you will fail already at this step instead of like having some network that then in the end is unstable. So that is my so I think that it's something I don't understand this completely, but I think either of these two situations will become real in such cases.
Okay, I see. Okay, thank you.
Are there any other questions? No, so let us thank the speaker once more. And then we can maybe set up the screen for the next speaker.